So this session today is about the chemistry of art, and I'll be presenting this to you. My name is Neve, and I'm a second year DPhil student in the Physical and Theoretical Chemistry laboratories here at Oxford, and I'm a member of Trinity College. So I just do want to start by saying that I am a chemistry DPhil student, so that's all very much within my wheelhouse, but I am not an art historian or conservationist. I just think that this stuff is really cool and interesting, and this intersection between chemistry and visual arts is what actually got me interested in chemistry in the first place. So I just want to take you through what my plan for the session today is. I'll just start off by saying that if you have any questions at any point, please do type these in the chat. If it's just a small diversion to answer your question, then I'll answer it there and then. But if it's a bit more of a substantial question, then we'll come back to it at the end. So what I'm really hoping to convey to you today is a bit of an overview about the ways in which what you might consider divergent areas of chemistry can come back together when you're considering real life problems and applications. So I'm going to take you through a few of the areas of chemistry that I think are particularly interesting in the context of visual arts, and really explore all of these in quite a overview kind of fashion, a real whistle-stop tour. So if you want some more detail on something, please do just ask, and we can come back to that during question time at the end. So the first area we'll be covering today is the history of science, and I'm going to give you a couple of examples that demonstrate just how connected the pigment industry and visual arts are. Then we'll actually talk about what happens in the eye that allows us to see light and art objects in the first place. Next, I'll talk about one of the mechanisms by which color, and particularly really intense colors, can arise. After that, I'll talk you through the physical chemistry of how some art materials are made and the different considerations that have to go into that. Next, we'll talk about how analytical chemistry and spectroscopy is actually a really vital part of analyzing existing famous art materials and trying to make good decisions about conserving and restoring them. Finally, I'll talk about a bit of maths and use the example of symmetry to give you a way of connecting a mathematical concept that was actually developed for the purpose of art and architecture and beauty primarily, that's actually, I think, quite surprisingly useful in chemistry. So with that, let's move on to a little bit about the history of science and the pigment industry. So I'd first like to give you a really classic example, which was the accidental synthesis of morphine. So the 18-year-old William Henry Perkin in 1856 was set with the task of trying to synthesize quinine by his supervisor. Lots of people at this point in history were really interested in synthesizing quinine because it's a really good anti-malarial drug that we actually still use to this day. The problem was, it was known how to extract it from natural sources, but their availability was not never ending. So alternative industrial synthetic routes were of a lot of importance to be able to treat the amount of malaria and its prevalence at this point in history. So Perkin did completely fail in his attempts to synthesize quinine, but during one of these reactions, which is the mechanism shown on the screen, he actually made something else that was also very interesting. So instead of ending up with the white powder of quinine, he got a bright purple powder mixture. And he realized immediately that this was not quinine, but that this could have real commercial use because it was such a vibrant purple that most people had never seen before. So he went through the process of getting a patent and setting up a factory. And that accidental discovery and synthesis actually pretty much started the pigment industry. This is widely considered to be the first synthetic pigment. And it was so successful that newspapers at the time were joking about people contracting more measles because they were just so obsessed with this color that they were wearing it constantly. Something else that might be interesting to you is the fact that this chemistry, so this is from the 1850s, actually wasn't well understood until very recently. So It took a long while to figure this out, but the purple powder that Perkin made was actually a mixture of a variety of different, very chemically similar molecules, but their exact structure wasn't actually totally found until the 1990s, I believe 1998. Also, the total synthesis of quinine wasn't developed and totally agreed upon as being a good synthetic route until 2007. So even though this might seem like old chemistry, it's kind of still happening now. The next example I'd like to talk to you about is Prussian blue. So this is a pigment you might recognize if you've seen Hokusai's The Great Wave and a variety of other Japanese Edo-era woodblock prints. And this is a really vivid, intense purple. Before the synthesis of Prussian blue, which there is a bit of debate about exactly when it was first synthesized, but the first pretty definitive synthesis was 1706. Before that point, the only blue pigment that was really available was ultramarine, which is made up of crushed up lapis lazuli suspended. So lapis lazuli is a really beautiful precious stone that at most points in history has actually been more expensive than gold. So you can imagine that only the absolute richest of the rich had access to this pigment. So the discovery of Prussian blue was actually something that opened up a whole new color to be used in the visual art space. Something else interesting about Prussian blue is that it was also totally accidentally synthesized at first. A Berlin chemist called Johann Jakob Diesbach accidentally made Prussian blue when he was actually trying to make a red dye, but one of his reagents was contaminated with blood, and the iron available in that blood allowed this complex, which you see a summary of the structure on the right. So now I'd just like to make my final point that's connected to sort of the history of chemistry and art, which is a bit less chemical detail, but something that I think is still really interesting, which is the invention of photography. So before the invention of photography, there's lots of reasons for doing art and purposes of art, but a widely agreed upon really major purpose was visual representation. It was one of the only ways of really capturing the visual world as a historical record. Once photography was invented, even the really simple single color photographs, like what you see on the left here, meant that visual arts no longer had to be about real representation. And the widespread proliferation of photography marks a real departure around the early 20th century, where a lot of art is focused more on emotion, it's focused more on conceptions, it's less concerned with actually gathering the photons and putting the image that makes in our mind and trying to translate that to paper. So if you'd like to learn more about the actual chemistry of photography, that's also something we can talk about in question time. Great, so I hope that little bit of historical background was interesting for you. We're now going to move on to what actually happens in our eye that allows us to see a painting or a sculpture. So let's start by thinking about what is happening at the object we're looking at. So there are lots of ways in which light and matter can interact. From the perspective of visual light, what you're seeing on the screen are the most relevant processes. So some materials are partly transparent, and we are able to see light that ends up coming through them. Some materials are like a mirror, are really reflective, so we are mostly just seeing light that is bouncing off the surface. When we have usually a rougher surface, we can get a lot of scattering, so the light is reflected but not in a coherent way. We can also have a material that absorbs a lot of the light that's falling on it, or that refracts through it or diffracts through it. And finally, if you're illuminating a sample at specific wavelengths, you can even get emission of light. Great, so we're just going to try a little quick pop quiz. I've got a little summary of the sort of modes of light matter interaction that are most prevalent. And I'm going to show you one piece of artwork. And if we could just get a few people to type in the chat what they think the most important mode of light matter interaction is, that would be great. So the first thing is an oil painting. So this is a painting by Australian portrait artist Nora Heysen. If you could please type in chat whether you think transmission, reflection, scattering, emission, absorbance, reflection, or diffraction are the most important modes of light matter interaction when we're trying to think about how this picture comes together. So I'll just give us about 10 seconds to give that a go. That's also, there is a chance the chat might not be working. So I will just move on from this one. But when we're trying to figure out where is the image coming from, the main thing we're thinking about with a painting is the reflection. Then this is the very beautiful stained glass window at the Royal Society of Chemistry. And in this case, we're looking, the light is mostly arising from, the color, sorry, is mostly arising from interactions where the light is just passing through the screen there. So yeah, that's perfect. Thank you. Transmission is our most important aspect. Okay, and there's a final one here. So this is Vantablack. So if you could please type in chat what you think the most important mechanism that's giving this appearance, that would be great. I'll give us about 10 seconds here as well. Yeah, perfect. Thank you very much. So absorbance or absorption are the most important processes here. So Vantablack is also a really cool pigment in and of itself. So we might take a second talking about it now. So you can see in this image, this is a metallic bust of one of the One Show presenters, I believe. And it's actually the same underlying substrate. These are two identical busts, and one of them has been coated with Vantablack. Excuse me. Vantablack is not something that you can buy as a pigment just in a paint tube, partly because the exclusive rights have been given to one artist, so you can't actually do that legally. But also, you actually have to use a chemical vapor deposition chamber. So you heat up this proprietary mixture, so it evaporates, and very slowly it deposits on the artistic surface. Vantablack is made up of a bunch of parallel standing up carbon nanotubes. So basically, when the light is incident on the surface, it gets trapped, bounces around, and only gets emitted as heat rather as visible light. So to us, when we look at Vantablack, it looks like it totally flattens everything because we're getting none of the reflections that normally tell us about the three-dimensional shape of an object. So yeah, Vantablack is a particularly cool pigment. Great, so that's sort of what happens on the side of the object that we're looking at. But what about when that light actually gets to our eyes? So there's a lot that goes on in our eyes and our brains to process visual information. So I'm just going to give you the real high-level basic overview. So we have light waves come into our eye. Our eye then has a lot of structures that help focus that light onto our retina. The retina is where light-sensitive cells called rods and cones are located. And we'll speak more in detail about exactly what happens there. But the short version is that they send out a chemical signal along the optic nerve, which sends the visual information to your brain, which can process it into an image, and then other parts of your brain, like the prefrontal cortex, make decisions based on that information. So let's have a little look at the rods and cones in a bit more detail. So that's what's happening there. I'm just going to show you the example of the rod. The cone is, of course, different, but it uses the same basic principle. So essentially, in the back of the retina, we have these rod cells. And within those rod cells, we have these biochemical discs. Then inside of those discs, we have rhodopsin molecules. And then inside of those rhodopsin molecules, we have retinal. So this retinal is a real important molecule to think about here. This is where the interesting chemistry happens. So when we have light of high enough intensity and of the correct wavelengths to be visible light, when they're incident on a rhodopsin molecule, the retinal actually absorbs a photon, which gives it just the right amount of energy to move from a cis retinal conformation, which is what you can see on the bottom left here, to a trans retinal on the bottom right. So that slight physical change in the orientation of the molecule puts pressure on the rhodopsin molecule that sends out a chemical signal. So that is a like physical process that happens in your eyes every time a photon of visible light wavelengths hits it. And then the rest of the cycle here is just showing you how that gets remetabolized, because these molecules in your eyes have to go back to the cis orientation so that they can continue to be used over and over again. And then in the case of the cones, their sensitivity to specific wavelengths is different, so that you build up this kind of red, green, blue picture of the world that your brain can process. Great, so that was the more biochemical side. We're now going to move on to thinking about how color itself arises. So we sort of talked about how light gets from being radiated from the sun or from a light globe, falls onto an object, and then gets back into our eye and into our brain. But what's actually happening at that object? We're going to spend some time thinking about that now. So the basic format in which we can understand visual information in front of us, either we're seeing the light that is coming off the surface, whether that be reflected or emitted, etc., or that's coming through a surface. There's lots of different mechanisms by which color can be created. So this kind of question mark of like what's actually going on in this material, we're going to talk about an example of that now. So I'm going to talk you through how color arises for transition metal complexes in solution. So this is a really specific example, and there's lots of other mechanisms by which color can be created. But this is one that you will learn about in some more detail later on in your A-levels if you haven't already. So I won't explain all the details, but if you'd like some more information, of course, feel free to ask in question time. So this is just to highlight to you, we're talking about transition metals specifically. There are other mechanisms by which color can arise. Okay, so you might have seen these diagrams before, but if not, don't worry, because I'll be talking you through it. When we have a transition metal ion, here that's represented by the letter M, in solution, it will generally be surrounded by what we call ligands. So these are molecules that coordinate in some way to your transition metal ion. Different ions and ligand combinations have a preference for different geometries based on a lot of quite complicated chemical reasons. But once you have that resulting geometry and you know it, which is something that you can figure out through a variety of spectroscopic techniques, you can actually plot out the energy levels of the d orbitals. So in transition metals, the other orbitals like the s and the p orbitals are already full. The d orbitals are what are only partly filled. So this y-axis here is representing an increase in energy as we go up the page. And it just so happens that for the transition metals, particularly in the first row, this gap between the two energy levels, and I should say these are the electron energy levels. So this is like the valence energy. And each of these boxes can contain 2 electrons, one spin up, one spin down. When electrons are excited by a photon, that photon energy happens to be lying in the visible light region. So that means that our transmission metal complex, if we're in solution, if we're shining a light through it, certain visible wavelengths of light are going to be absorbed. And you can do a lot of really detailed calculations to figure out exactly what wavelengths will be absorbed. I will also say that this is an example of crystal field theory for transition metal complexes. There are more complicated and more accurate alternative theories and models as well. But just to give you an idea of how much variety this gives us, on the screen now are some examples of the different colors of transition metal ions as complexes in solution. So yeah, there's a really massive variety, and these colors are also usually really intense. Okay, now that we're roughly halfway through, I just wanted to give you guys an opportunity to have a very quick question break. So if you need to grab a cup of tea, you've just got a minute to do that now. And I wanted to ask if any of you guys have a favorite artist. So this is very broadly defined. It can be a painter, a musician, someone in film, an actor or an actress. And I'll just give you about 30 seconds to type something in the chat if you'd like to contribute. I'm just curious to see. Picasso, good choice. He's featured already today. Again, another good choice. My personal favorite century for visual arts was probably the 20th century. So I can definitely see the appeal. Basquiat, also great choices. Yeah, I'll give just another 30 seconds for other people to contribute if they would like. You can also not have a favorite artist and tell us that if you just like quite a lot of stuff, but nobody's quite your favorite. Okay, 5 more seconds. Great, and yeah, feel free to contribute in chat as we go if you would like to. But for now, we're going to move on to the next section, which is talking about the physical chemistry of art materials. So there are an awful lot of choices that you have as an artist or anyone making anything really of how you're going to go about making your art. So for example, are you going to make it on paper, on canvas, on film? And then what are you applying to that? Are you going to use paint, pencil, crayons? Are you going to do something totally different and make ceramics? There's a whole lot of chemistry that goes into all of these combinations. So I thought today, so that we're not here for 5 hours, I'd just tell you about my favorite one, and that is paint. So paint, probably you're familiar with lots of different types of it. In school, normally you use like plastic acrylic paint or watercolors. And if you go into an art shop, you'll see there are tens of varieties that are regularly available. But the actual basic composition of paint is the same, really, on each occasion. So you have a pigment. So this is something that's highly colored. For example, the Malvine or the Prussian blue that we spoke about earlier. And then you suspend that pigment in a medium of some kind. So that's some kind of a liquid that can carry your pigment. And when you mix that together and you get everything right, you get beautiful paint. So there's a lot of detail that actually goes into making a really good paint. So we won't even have time to get into every single variable that you have to think about to optimize this here. But I'll just give you a bit of flavor for the variety that artists have access to through the work of chemists. So something that's been a favorite medium throughout a lot of recent centuries is oil paint. So that's when we have a medium that consists of oil and a few additives. The way that something that's also important to think about when we're thinking about paint is that at some point we want it to go from an applicable fluid that we can move around our page or canvas however we please to something that will stop flowing so that when we hang it up on the wall, it won't just all drip off. Unless you like dynamic art, I suppose, in which case you might not be interested in that. So there has to be some way that the medium goes from being a liquid carrier to a solid matrix that holds the pigment in place on the substrate. So in the case of oil paint, the oil slowly reacts with oxygen and moisture in the air to polymerize. So instead of being free fatty oil chains, they start linking together and that forms this nice solid matrix. Now that's actually a really slow process. For a really thick oil paint that it takes air a while to sort of permeate, it can actually take years for the painting to dry. So from an artistic perspective, that could be amazing. That means that you can work on your painting week after week, and you'll still be able to blend the colors together and make revisions. However, not everyone likes working like that, which is where watercolor comes in. So in the case of watercolor, the pigment is suspended in an aqueous solution, the main component of which is something called gum arabic. So watercolors dry a lot faster because essentially all that really needs to happen is for the water to evaporate, and then the gum arabic is kind of what it says on the tin. It's a gum that kind of solidifies pretty quickly. So that's something that, depending on the artistic decisions you're going to make, this exactly how the paint forms is actually really important consideration. Finally, acrylic paint is probably what most people are most likely to have worked with. And this is actually quite a complicated water-based emulsion of acrylic monomers in solution. And as the water evaporates, we get cross-linking of these as well. So based on a very similar principle to oil paint, but this process, because it's depending on that water evaporation, is much, much faster, usually on the scale of minutes. So you might have noticed earlier that I used the phrase suspension. So the pigment is suspended in your medium. There is a very particular reason why I said suspended and not dissolved. So this is just a concept that if you end up coming to Oxford and doing chemistry, you'll learn about colloidal suspensions in quite a bit of detail. So I'm just going to take you through the differences between a solution, a colloid, and a suspension. So hopefully that makes a bit of sense. And then we'll talk about what makes a good paint. Is it a solution, a colloid, or a suspension? So in a solution, we have some kind of ionic or very small covalently bonded molecules that are evenly dissolved and dispersed throughout the solution. In the case of a colloid, we have larger particles. I think usually the range that people go up to is in the range of hundreds of nanometers or even microns wide. And these are also evenly suspended throughout solution, but they're not purely molecular components. They're usually lots of molecules stacked together into a nanoparticle or a micron-sized particle, for example. And then finally, we have something like a suspension. So this is where we have some kind of solid material, although you can actually have liquid in gas suspensions and things like that. In our case, for paint specifically, we're only worried about solid in liquid. And when you leave that on the side of a bench, the solid will gradually settle back out. So that might be something like coffee, where if you're taking a long time to drink your coffee, you end up with these solid coffee grains at the bottom of your mug. So with that in mind, we can have a think about what is best for creating a good paint. If we have just a solution, then once we say strike our brush across our page and the water evaporates, we're only left with these, small ionic fragments behind. It's quite hard for those to be really colorful. So actually a colloidal suspension is really good, where we can have these larger sort of pigment globs that when our solvent evaporates or we get this polymerization, there's those highly colored pigment particles are left behind. And then finally, in the case of a suspension, that's probably not going to be very nice to work with. If you've ever had a really old tin or tube of paint that you've left out in the sun that hasn't been stored correctly, this can actually happen, where you end up having all your pigment at the bottom and then just the liquidy, gross stuff at the top. So how do chemists figure out what is going to be a nice colloidal suspension rather than a gunky, more generic mixture or suspension? So this is just a very basic picture of the two main things that you have to think about to have a nice, stable colloidal suspension. On the left-hand side, we have these highly colored pigment particles, which are represented as this bright orange, and then they're suspended in this solution of some kind, which we're representing with the light blue. In a good colloidal stable suspension, these particles will be repelling each other enough that they're going to stay away from each other. So on the right-hand side, we're seeing the situation where we haven't tuned our solution and our particles appropriately. So they all end up clumping together or coagulating. And usually that will make them dense enough that they'll end up falling out of the solution and collecting on the bottom of our container. One thing that we have to think about is we need to make sure our particles are repelling each other enough that they're overcoming any inherent attraction they have to each other. So one way to do this is to make all of your particles the same charge. So say you have all positive pigment particles, that like electrostatic repulsion will help keep them away from each other. But if you have particles that aren't as highly charged, when they bump into each other in solution, they might end up experiencing van der Waals attraction and sticking together. And that's where you get this undesirable situation. Great, so that's all I wanted to say about the physical chemistry of paint. Now I'd like to talk a little bit about analytical chemistry and spectroscopy and how that's useful in the art world. So one thing that you need to think about if you're doing anything analytical, really, it's kind of like being a detective. You're trying to figure out exactly what's going on. And a really important part of being that detective is actually understanding how all of the components stack together. So in the case of a painting, we've got the beautiful Mona Lisa here, for example. We need to think about what's actually happening with the cross section, because all we're seeing is the final painting. And in most paintings have quite a lot going on. There's a lot of layers. So I'm just going to talk you through the most common layers sort of in the last couple of centuries of painting that have to be thought about. So usually we have some kind of physical solid support, like a canvas frame or like a block of wood. Then there's some kind of a ground. So this is some kind of material like canvas or paper, which has nice properties that it imbues in the final art. That's how people usually choose. And then often there's a primer of some sort applied on top. So this is something that makes the ground easier to work with if you're doing a painting, for example, and is something that the paint will stick to very nicely over time. Finally, a lot of artists will do an underdrawing or painting of some kind of their sort of plan. And then we get, sometimes not many layers of paint, sometimes lots and lots of layers of paint, and some kind of a varnish on top. So this is usually a shiny plastic-like layer that helps protect the painting underneath. So that's all well and good. Normally, we're just seeing the result of all those summed layers of paint, and we can't actually see the underpainting or drawing underneath. You can imagine that for really famous artists, where people are really interested in how they did their paintings, this is something that would be really interesting to know about culturally. So that's one thing we're going to talk about. How do you get to that underpainting or drawing using non-destructive chemical techniques? And there's actually lots of ways of doing that. The second thing that I want to talk about is the fact that when we're thinking about reactions in class, often we only really care about the reactions that happen on the scale of time that we're in the lab. So the reactions that happen in minutes will happen. The reactions that happen in days and years, we usually don't really worry about. But paintings are actually a really interesting case where sometimes a painting will have been preserved for centuries or even longer in the case of cave paintings, millennia. And that means that these really slow reactions actually become really important because we're looking on such long time scales. And sometimes these layers can react with each other, which can make it really challenging to get to the heart of what the painting originally looked like as the artist intended. So first, I'm going to tell you about an example where this reaction rate problem, so thinking about these slow reactions, is actually quite interesting. So here is a screenshot that I took from this CNN article, which is really excellent. I'll give you a link at the end of the presentation as well if you'd like to go read it. I do really recommend it. On the left-hand side is Vincent van Gogh's painting The Bedroom as it looks today if you were to go to the National Gallery in London and have a look. on the right-hand side is a digital restoration of sort of scientists' best guess of what the artwork looked like when it was first painted. So the reason that this kind of back calculation, this estimation of what the painting used to look like is possible is because Van Gogh actually wrote in a huge amount of detail what pigments he was using in his paintings and where to his friends and family. So I'm not sure that every member of his family loved hearing that level of detail about his pigment choice, but it's really useful for scientists who now have access to those letters because now they know, okay, this is what we started off with the painting. This is what we ended with. What happened in between? So Van Gogh's paintings, because he gave so much detail, are actually being really helpful for chemists to understand these really slow reactions and how they progress over time, because they can see the decomposition products. So I'm just going to talk to you about two of the specific pigments of interest here. One is carmine, which was used primarily in the walls. Originally, the walls looked quite purple. Now they look quite blue. That's because carmine's a red pigment, and over time, it started to degrade. I wasn't myself able to find detail on the exact reaction mechanism, and I'm not sure that it is known yet. But given what we talked about earlier with transition metal centers often being where the color is really coming from, the important electron transitions that allow us to see that color, probably we're having something happen around this aluminium where as the painting is exposed to air, slowly we get a breakage with one of these bonds that changes the geometry around the transition metal ion and thus will change its color. So we're losing all of the nice purpliness of those walls. Also, the floorboards contain a lot of eosin, and I believe it's the Y version of this compound. There's also another version that's very subtly different. So if you're interested in that, have a little look at the article and also the Wikipedia page for eosin. But this starts off as a nice, pretty pink, but gradually with time, the bromine ions have become free, and bromine by itself is a very distinct brown color. So this decomposition is also really changing the appearance of the painting as it is today. So you might be wondering, given that we know this and have quite a lot of detail, why would we not just fix the painting? With such famous works in particular, there's actually like a lot of decision making and thought that goes into what really would restoring this painting be? Would it be changing the painting as it's been seen for the last 30 or so years? Or would it be bringing it back to what we're pretty sure it looked like a century or so ago? So that's where this idea of digitally restoring, so having some imagery that mimics what the painting would have looked like, can potentially be the best of both worlds. Also, in the studies that they did on this particular painting, excuse me, sorry, as well as some of Van Gogh's other paintings, he uses a lot of yellow lead chromate pigments, which also fade with time. They end up becoming less intense yellows. And that has changed the way that these artworks are displayed. They're usually displayed in very low blue light conditions because it's blue light that happens to accelerate that lead chromate decomposition. Great. Now I want to talk to you a little bit about the discovering the underpainting aspect of studying an artist's work. So this is one of my favorite artists. It's Surrealist René Magritte. And he was a Belgian artist at the start of primarily working at the start of the 20th century. And one of his paintings actually went missing at one point during the 20th century. There are some records of it and black and white photographs of it in some art history textbooks from the time, but it seems like around World War II, no one really knew where it went. And by analyzing this painting, which is a sort of abstract surrealist painting, using X-ray imaging, they actually realized that that's where the hidden painting had gone. It what had been lost was actually hidden underneath all these other layers of paint. And by using X-rays, which are able to permeate through quite thick layers of paint, they were able to see some signatures of what this underpainting looked like to be able to identify it. So this is just a zoomed in version of that image there. And I thought it'd be interesting just to tell you a bit about the specific technique they used of X-ray fluorescence analysis to give you a little bit of a flavor of how they do such accurate summaries of what that painting looks like underneath. So because light and matter interact, which is how we see visual light in the first place, we can actually exploit that using other wavelengths of light to see information that we can't see with visible light. So in lots of scenarios, like getting an X-ray on a broken bone, or trying to see what's underneath a painting, or even looking at cracks in aviation vehicles, X-ray wavelengths are actually really useful. So the core mechanism here is that if we shine X-ray radiation, which will be of some particular wavelength that we know precisely, that's enough energy to kick out a valence electron. So in this case, it's the K orbital. So we have an electron that goes flying off. One thing we can do is look at the energy and the positioning of that electron, but something that's often easier is looking at X-ray radiation that comes back out of the surface. So once we've kicked an electron out of the valence orbital, that is not energetically favorable for that atom or ion. So we have electrons falling back down further energy levels. That extra energy that they've lost has to go somewhere, and usually the change in energy is small enough that it means we get X-rays back out. And that signature tells us very specifically about the energy levels of these inner orbitals in an atom. So we get really specific fingerprints for specific atoms. So oftentimes the painting underneath will have a different pigment composition, different elemental composition to the painting on top. I also just wanted to mention that if you find this conservation and restoration process really interesting, then it's worth having a look at this article that I found by Business Insider, where they take you through the step-by-step technique that a conservator used to restore a painting. So it came in looking like the right half of this image here, and came out looking like the left half of the image. I also, so one problem with this particular painting is that it was like hanging in a living room where people smoked a lot. So there's actual soot deposited on the surface, but also paintings from lots of points in history before about 50 years ago used a lot of lead carbonate and lead hydroxide, which is represented down here, which when exposed to even very small amounts of sulfur compounds in the atmosphere, react to form lead sulfide, which is dark black. So you get a real progressive dulling of a lot of whites with time. Also, because those lead compounds are really toxic, you can see on this image on the left that the conservators work in a very scientific environment. They're having to really think about chemical compatibility, chemical risks, and it's a real interesting combination of having a chemical understanding and a sort of artistic understanding of works, because you really do have to just make choices about what the best way to do something that is faithful is. Great, and I'm just going to bring us on to our final area of discussion today, which is symmetry as an example of a concept that was developed mathematically, kind of motivated by artistic intent, that's also really interesting from a chemical perspective. So on the left-hand side here is a picture of the Parthenon on the Acropolis in Athens. So this was built during ancient Greek times, and there's an interesting feature that they built into the architecture of the Parthenon, which is that if you are looking from below the Acropolis, The Parthenon looks perfectly straight up and down, and all these columns look perfectly parallel, and it all looks beautifully symmetric. But when you get up close, you'll see that the columns are actually a little bit bent away from you. And that's actually something that they figured out through doing very detailed mathematics, that they could make the Parthenon, which would mostly be seen from very far away, look very symmetric, and in their eyes, more beautiful. It's also, even into the 20th century, artists were interested in using mathematics to create interesting compositions. M.C. Escher is a great example of this. He has a lot of really interesting art, some of which are these tessellations of animals. So he was actually friends with lots of mathematicians who would give him different tilings that he could play with and, for example, draw lizards on. And he also did some really interesting sort of architectural optical illusions. So there's been interest in this from a kind of beauty in the eye of the beholder perspective, but thinking about molecular symmetry is also actually a really insightful from a chemical perspective. So I'll just give you one example of how that's useful now. So this molecule is formaldehyde, which is a nice simple molecule example. And on the left-hand side is a diagram of the different symmetry elements of formaldehyde. I won't go into detail on the different types of symmetry that exist in molecules, because if you do come to Oxford, you'll spend quite a lot of time on that yourselves. But basically, when light and matter is interacting, there are certain rules that govern when absorbance or emission can happen. So those are called selection rules. In the case of having IR radiation incident of a molecule, usually that's infrared radiation. Usually infrared radiation is of an appropriate energy to just vibrate the molecule a bit. It won't break apart bonds or do anything crazy, but you'll just have, instead of having, fairly static CO or CH distances, they'll start to go in flux in specific ways. So the selection rules, once you learn a bit about them, also, which if you come and do undergraduate, you'll do all the maths for, basically tells us that that will only happen when the molecular symmetry is such that changes in those bond lengths and angles will change the dipole moment of that molecule. So on the right-hand side here, these dips are where the infrared radiation is actually able to do that, so modify the dipole moment. And that is incredibly specific to different molecules. So essentially, from having the symmetry bound what's possible for the molecule, you get a really distinct fingerprint. And that's also useful for art conservationists, conservators, because IR radiation is also a way that you can figure out what is actually in the painting you're trying to restore by identifying all sorts of different chemicals. Great, we're coming towards the end of this for today. So I just wanted to point you in the direction of a couple of different activities or extra readings you could do if you found this interesting. I would first like to really highly recommend the chemart.rice.edu website. So this is a collaboration between Rice University in the United States and an art conservator organization. And I used a lot of this information to help me put together the presentation for you today. Also, I'd really recommend seeing if you can find a way to watch Ways of Seeing by John Berger. This was a 1970s BBC documentary that talked about sort of how perspective and the eye and the way that vision works really affects how art impacts us. And this kind of exploration of ways of seeing, which is kind of what we were talking about earlier on, pretty much changed the way that art criticism and curation was done. Next, if you found that Vincent van Gogh example interesting, you can read the whole article. And finally, if you want to learn more about pigments and you're really, really keen, I super highly recommend reading Chromatopia by David Coles. So this is one of my favorite books of all time. The photography is amazing. It's all about the history and the chemistry of pretty much all compounds that have been widely used in human history. And it goes all the way from sort of prehistory and cave paintings to today.